In this video, I'll teach you to use the four kinematic equations, which you're going to use very often later on. And they're used when acceleration is constant and unchanging. So there's four kinematic equations in total, and they all serve different purposes. Here's how the video is going to go. I'm going to derive the equation really quickly, and then I will go through an example. Now, the reason why I'm going to derive the equation first is because it's good to know where it came from, as in the future you might need to be rearranging them, and this knowledge is extremely fundamental. Let's start with some notation. So as you know, average velocity is delta x over delta time. This is equal to x2 minus x1 over t2 minus t1. But we're going to change the notation for these kinematic equations. We're going to use final velocity as just x by itself. Take away initial velocity, which we're going to call x0. Same with time. We're going to do t minus t0. T0 is usually numerically just 0, because imagine you have a stopwatch and you click start. It starts at 0 seconds, so we're just going to write it as 0. So our new average velocity equation is x minus x0 over time. Next step, we have average acceleration is equal to velocity minus initial velocity over time, assuming acceleration is constant. If you notice, this is in the same format as these up here. Now with this new acceleration formula, we can do some rearranging to find velocity. So let's multiply both sides by t, and we get at equals v minus initial velocity. Add v0 to both sides, and you get velocity is equal to v0 plus at. This here is the first kinematic equation. I highly recommend you write down the kinematic equations. They are absolutely everywhere in the field of mechanics. Let's run a quick example with our new equation, which, if you remember, is v equals v0 plus at. A quick note, if you see v0 here, some textbook notation, they prefer to write initial velocity as u. So if you ever see velocity equals u plus at, just remember that u is initial velocity. However, in a lot of textbooks, it's also v0. v0 makes more sense to me as the starting velocity, so that's what I'm going to use. Now imagine a skateboarder skates at 4 meters per second, and he decides to speed up at 1.5 meters per second squared for 4 seconds. What is his final velocity? So how fast is he traveling after this acceleration? Let's do it. So take this equation for final velocity. Velocity equals initial velocity, which is 4 meters per second, plus acceleration, which is 1.5, multiplied by time, which is 4 seconds. Run your calculations and you get velocity is 10 meters per second. So after this quick acceleration period, he is skating at 10 meters per second. Now for the second equation. The second equation is for average velocity. Average velocity is usually just simply delta x over delta t. But in the context of kinematics equation and constant acceleration, we can write it as v0 plus v over 2. This means the average velocity is simply halfway between the initial velocity and the final velocity. Halfway. It's the average. So here is the second kinematic equation. Now for the third equation, it's going to take a few steps. How would you find the position of x after it undergoes constant acceleration for a time t? Well, let's take our very original average velocity equation, not our new one that we created. Average velocity is placement over time. Let's solve for x. So multiply both sides by t, you get vt equals x minus x0. Add x0 to both sides, and you end up with x equals x0 plus vt. The next step is to plug in our second kinematic equation, which we just derived, which is v0 plus v over 2. We're going to plug this guy in right here. So that gives us x equals x0 plus velocity 0 plus v over 2 times t. pay close attention here. We're going to plug in one more equation. I know it's a lot, but here, see this velocity. If you remember our first kinematic equation, velocity equals velocity 0 plus at. We're going to plug that in now. So that becomes v0 plus v0 plus at multiplied by time. Next, we're going to expand this bracket, and this is our third equation. X equals x0 plus v0t plus 1 over 2 at squared. This is kinematic equation number 3. Make sure you write this one down because this one, I see it everywhere. It's used very, very often. Now for the final equation. It's useful in situations where time is unknown, but you want to find things like velocity and displacement. This final equation does that. Now let's take this equation for x. Here we can plug in the second kinematic equation. So let's do that. We get x equals x0 plus v0 plus v over 2 times t. Now how's this going to help us solve stuff when t is unknown? T is still in the equation. Well, let's fix that. Take the first kinematic equation and rearrange it for t. First, minus velocity from both sides. Then divide by acceleration. Then you end up with time equals velocity over acceleration. We're going to plug this in here. So now we end up with this juicy big equation. Expand this stuff and you end up with x equals x0 plus velocity squared minus initial velocity squared divided by 2a. Now this isn't quite the final kinematic equation. If you went and rearranged the equation and solved for velocity squared, it would end up as velocity squared equals initial velocity squared plus 2a displacement. This is the final kinematic equation, and it's used when you don't know time, but you have stuff to solve. Now really quickly, take a look at this equation. Let's subtract x0 from both sides. This becomes x minus x0 equals velocity squared minus v20 over 2a. This right here is a variation of this equation. However, it finds displacement instead of velocity. Here is a quick recap of every equation. First, we have the velocity equation, then the displacement equation, the velocity equation when you don't know time, and the average velocity equation. Please understand this. These equations are not valid. They do not work if acceleration is not constant. So these kinematic equations, these 4 equations, they only work when acceleration is uniform and unchanging. And remember, depending on your textbook notation, or maybe you're taking a course at school, depending on the course notation, sometimes initial velocity is u, and displacement is sometimes d or s. So keep that in mind. Okay, let's do some fun examples now so that the concepts can click for you. So you have a small plane, and to take off the ground, it needs to reach a velocity of 50 meters per second. Plane on the runway accelerates at 3 meters per second. The question is, how far does it have to travel to reach this takeoff velocity? First, let's identify what exactly we're looking for. We're looking for the length of runway required for the plane to reach this takeoff position. So basically, displacement. Now flip back through your notes. Which equation gives you the displacement? The equation is x equals initial position plus initial velocity time plus 1 over 2 acceleration time squared. Let's identify our variables. So initial position, we can just write as 0. The initial velocity, since it's starting from rest, it's also 0. Now the acceleration is 3. And it seems we're missing something. We don't know the time. We don't know how long it takes. So let's take a step back and quickly solve for time. Let's use the first equation this time. So velocity equals VO plus AT. Let's rearrange the equation for time. So T equals V minus V0 over A. Now let's plug things in. The velocity is 50, so 50 over 3, which is roughly 16.67 seconds. So the time needed to reach takeoff speed is 16 seconds. Let's plug that in here. So 16.67 seconds. Run the calculations and X comes out to be roughly 416.83 meters. So if you were to design a runway for this airplane, how long would you do it? Well, me personally, I would give it a good 450 meters of space to take off comfortably. Now I'm going to give you your own problem to try and solve. Get ready to do some thinking. So we have a bike and it starts at rest and accelerates at 2 meters per second squared for 5 seconds. And then it travels at a constant speed, for another 3 seconds. The questions: find the velocity after 5 seconds. So this quick acceleration phase here. And the second question I give you is total distance after the entire 8 seconds. Pause the video, go ahead. Now let's solve it together. So the final velocity after this acceleration phase, we're going to use the first kinematic equation. So velocity equals initial velocity plus AT. This is equal to 10 meters per second. So after 5 seconds, he's moving at 10 meters per second. The second part of the equation is the total distance. So we're going to use the kinematic equation. X equals x0 plus v0t plus 1 over 2 at squared. The initial position and initial velocity, a lot of the time in textbooks and problems, they are completely skipped over because majority of the time there's 0. So if you ever see just this, then understand that it's because the initial position and velocity are 0. Let's plug in our values. X is equal to 1, 2 times 5. So that is equal to 25 meters. So after 8 seconds, the bike moved 25 meters. The final example I'll go through today is important. This example will teach you how to find velocity when you don't know the time. So here's the problem. You have a Ferrari. Here's your beautiful Ferrari. It starts from rest and then it accelerates at 3 meters per second squared. And it does this for 75 meters. The question is, what is the final velocity of the Ferrari? And the second part of the question, as a bonus, is how long did it take? So the equation that we use when t is unknown is v squared, initial v squared, plus 2a x minus x0. Let's plug it all in. So since the Ferrari starts at rest, the initial velocity is 0. The acceleration is 3 and the displacement is 75 meters, which we get from here and here. Go ahead and solve it. You get velocity squared is 450. So velocity is root 450. Put it into a calculator and it's 21.2 meters per second. That is the velocity of the Ferrari after this acceleration period without knowing the time. Now let's tackle the second part of the problem. How do you find the time taken? Well, it's easier now that we know the velocity. Now, if you rearrange the average velocity equation to solve for time, you get t equals x minus x0 over average velocity. And you might think, oh, we can just plug this in. No, we can't because this is the final velocity. So let's find the average velocity. Remember, when acceleration is constant, the average velocity is halfway between the starting velocity and the finishing velocity. So v minus v0 over 2, which is 10.6 meters per second. If you notice, it's half of the final velocity. So 10.6 meters squared, we're going to plug this in here. We're also going to plug in the displacement. And the answer is 7.08 seconds. So the Ferrari, after accelerating for 75 meters, is moving at 21.2 meters a second. The time it takes to accelerate to that speed is 7.08 seconds. To get